Hello everyone. Welcome to a graphics math video, or Manimation, that demonstrates one of the many proofs for the Pythagorean Theorem. The point of this is to help visualize and understand, geometrically, why the Pythagorean Theorem holds true. This theorem is probably one of the most cited theorems to generate, utilize, and solve other equations and problems in mathematics. So to get started, what exactly is the Pythagorean Theorem? You might have heard of it before, but it all boils down to a squared plus b squared equals c squared. This might seem simple, but what is a, what is b, and what is c? How is this equation even formulated? Well, first, let's look at a right triangle. A right triangle consists of two legs and one hypotenuse. The hypotenuse is the longest side and opposite to the right angle, and we give it the term c. The legs are each a and b, and it doesn't matter which letter we give which leg, just as long as you stay consistent. It's also important to remember that this theorem only works with right triangles. Right triangles are signified with a small box at the region on the inside of the triangle where the legs intersect. Now that we know what a, b, and c are, let's move on to the proof. Let's first imagine a large square. Let's draw another inscribed square inside of the bigger one. It's important to note that the angle of rotation relative to the horizontal axis of this inscribed square isn't important to the proof. Let's call each of the sides of the square c. When we draw this inscribed square, we're also leaving four congruent right triangular regions. If you're curious, these triangles are congruent by angle side, with the right angle, one of the acute angles, and the hypotenuse as c. Let's call the longer side of each of these triangles a and the shorter side b. We see that each right triangle follows the notation we previously discussed, with both legs being a and b and the hypotenuse being c. Now let's think about what the area of the inscribed square is. The area of a square is the square of its side length, and in this case it's given as c. Therefore, this area is c squared. We will call this area a sub square. Now let's think about the area of the full square. We will call this area a sub full. We know the area of the full square is the square of its side length, but we don't have a number for its side length. So we should just use the sum of a and b as a full side. So to calculate the area, we get these two equations and we substitute a plus b for s. Once we do this, we will get a sub full equals to a plus b squared. Now if we simplify with binomial theorem, we will get a plus b squared equals to a squared plus b squared plus 2ab. If you're not sure what the binomial theorem is, try writing the square as a plus b times a plus b and FOIL it. Now we have a simplified expression for the area of the full square. Let's save it in the top. Now, we know the sum of the inscribed square plus the sum of all four triangles will give us the full area, so we can express that idea with this equation. We already know from before that the area of the inscribed square is c squared, so now we can substitute. Now we need to calculate the area of the triangles. To do that, we can rearrange them a little bit. We can see that we get one full rectangle with length a and width 2b. The area of this highlighted rectangle is equivalent to the area of all four triangles, and this area, by length times width, is 2BA, or 2AB using associative property. We can substitute 2AB into the equation for a subtriangle, and then substitute the value we saved into the top right for a sub full. Now we see that both sides add 2ab, and we can subtract this value from both sides, maintaining equality, leaving us with our equation, a squared plus b squared equals c squared.